Okay, let's go through the contents of this video. First, I will explain what is the need of the controllers. Then I will explain the basic controllers types such as proportional, integral and derivative controllers along with their properties. Then I will explain the controller combinations such as PI, PD and PID controllers and their properties. And later we will see that how we can design the controllers in MATLAB, followed by the MATLAB code for design and implementation of these PI, PD and PID controllers. And in the last, I will do a comparative performance analysis of these controllers. So let's start the session. First, let's see what is the need of these controllers. So actually the performance of any system is usually analyzed on the basis of the few parameters. So these parameters are of time domain as well as of the frequency domain, and following are these parameters. So in the time domain, we have the rise time, maximum overshoot, settling time, steady state error. And if you see the rise time, the lower is better, and the lower value of the rise time makes system response faster. Similarly, the maximum overshoot, that is also required lower value, and the lower value of maximum overshoot makes system more stable. And similarly, the settling time is also required of the lower value, and its lower value makes the system to settle faster to its the final value. And then steady state error, of course 0 is required, and the output reaches to the desired value if the steady state error is 0. And in the frequency domain, we can see that we have the phase margin whose higher value is desirable, and its higher value actually creates more stability margins. So it means our system is more stable. And we have the gain crossover frequency and the phase crossover frequency omega g and omega p. And this is the desired relationship between the omega g and omega p. I mean, the omega p must be greater than omega g to make the system stable. And actually, when we design a system, so we get some transfer function. And after testing this transfer function, we see that the output which we are getting from this system are not satisfying our requirement. So we can actually analyze the response of that system on the basis of these parameters which I have already discussed. So now if you want to change the system response according to your requirement, then what we can do? You cannot change the system transfer function g again and again. So for that, actually the controllers are used to change the system response as per our requirement. So you can see that controllers are actually the system's response modifiers. A controller is introduced with the main plant transfer function in the feed forward loop as shown below. So here you can see that this is your plant transfer function GS, whose response you want to modify or change according to your requirement. And this is the controller which will do that work. So the GC will change the response of this transfer function GS, and by inserting this GCS, we get a overall transfer function of this plant or system, and then we check for its output for different inputs. If again we are not getting the response as per our requirement, then we have to tune this GCS, I mean the transfer function of the controller, to get the system response what we actually require. So now let us go to the different types of the controllers. Actually here I am taking only analog continuous time controllers. We have a few basic controllers such as the proportional controllers, and then integral controllers, and then derivative controllers. With the help of these basic PID controllers, we can have the various combinations of these controllers, such as the proportional plus integral controller, that is known as a PI controller, and then proportional plus derivative controller, and then proportional plus derivative plus integral, that is known as the PID controller, which is the most popular in the control system theory and applications. So now let's go through each controller one by one. So first I'm taking the proportional controller. The proportional controller is simply an amplifier. So it has a constant gain. So its transfer function is GC as equal to KP, that is your constant. So obviously it does not add any new pole or new zero to the system, and this is your controller. So EIT is the input error to this controller, and E0T is the output error, and capital EIS and capital E0 as are their frequency domain representation. So this is the time domain equation. So here you can see that output of the controller is simply the KP times input error. So that means the input error is amplified by the factor KP, and this is the frequency domain equation where you can find the transfer function, GCS of the controller. So that is E0 S upon EIS is simply the constant KP. So with the P controller, the response of the closed loop system becomes more faster, but the maximum overshoot also increases, and the large value of KP can make system unstable. The P controller also cannot handle the steady state error, and it also gives the offset error. That is the main drawback of the P controller. So now let us go through its performance comparison. So for this we have taken the plant transfer function, this one GS, that is 5 upon S plus 1, S plus 2, S plus 3. So this plant has 3 poles, all are on the real axis, and we want to modify the response of this system GS. So when we make a closed loop system with a unity feedback, we get this type of output. So this is my plant response without controller. So this is without the controller. So here you can see that I'm getting this response which has the huge amount of steady state error. So it's the final value is 1 because of the unit step, but it is settled at somewhere 0.46 something. So there is a huge steady state error with this system only, but when we introduce the P controller, we get this type of response. But as I said, the P controller, they also cannot handle the steady state error, and also they give the offset. Still I am not able to get ESS 0, so still I am getting some ESS in form of offset of this controller. But one good thing I am achieving here is that my system response has become faster. So you can see that the rise time TR is now reduced for this red color, the P response. So my system has become faster, but at the same time, if I compare the maximum overshoot, that has also considerably increased. So, and I also got a few oscillations. So here you can see that although my system has becomes faster, but the P controller itself again not able to reduce the steady state error to the 0. Also its transient is slightly disturbed. So now let us go to the I controller, integral control. So its transfer function of the controller is GCS equal to KI upon S. So because of the integration, of course, this is 1 upon S. So by adding this, of course, it adds a pole to the overall system, and hence it increases the system order by 1. And you can see that this is the time domain equation of your controller. So the input error EIT is integrated and then multiplied with some gain KI, and this is the frequency domain representation. So here you can see that transfer function of the controller is simply KI upon S. With the I controller, the offset error given by the P controller can be removed completely, and the steady state error in the step response is also eliminated. So the I controllers are very good to make the ESS 0. However, the system response becomes slightly slower. That means the rise time becomes slower, and the oscillations in the system response also increase, and the maximum overshoot also increase. So that can make the system unstable. So let us compare its response with the uncontrolled system. We are taking again the same plant transfer function, and this is our controller transfer function. So ki here is 0.369 upon s, and this blue one is again your uncontrolled system response. And here you can see that we are getting the Hughes ESS. We are getting the Hughes ESS, but with the I controller, we are getting this response. And here you can see that this response has reached 1. So the steady state error is now 0. So that's the beauty of the I controller. But at the same time, there is a decrement in the speed. I mean, your rise time has increased. So your system response becomes slightly slower. Also, there is a slight increment in maximum overshoot. Okay, so that is the response of your integral controller. Now let's see the D controller. That is a derivative controller, and the transfer function of the controller is simply KD as. Obviously, because of this as, it adds a zero to the system. So it modifies the system transfer function. And this is the time domain equation of your D controller. You can see that the output of the controller is simply the derivative of the input error multiplied with the gain factor KD. And this is in the frequency domain. So the transfer function GCS is simply E naught S upon EIS, that is SKD. So this D controller actually gives the faster action when the input changes rapidly. However, the D controllers are never used alone, because if error is constant, suppose your error is constant, EIT, then what will be the output of your system? Your output of the system E naught T will be 0, because the derivative of the constant function is 0. So the output of the controller is 0. If output of the controller is 0, obviously the actuator will not do anything, and there will be no action in the system even though the error is present. And also, if error changes suddenly, such as this is your error before t equal to 0, and suddenly it goes to some higher value. So what will be the output? So this is your input EIT. So what will be the output? Obviously the derivative of it. So you get an impulse delta t at this discontinuity. So this is your output of the controller. So there is a sudden action we will get as the output of this D controller. So that is impulsive in nature, and because of this impulsive output, the actuator can give a sudden action to some system components, such as applying a force on particular valve or something else. So that will also happen suddenly. So that can break that system components. So that's why the D controllers are never used alone. So we go for now the combinations of these controllers. Combination because as we have seen that P controller has some advantages and some disadvantages, while that disadvantages are removed by the I controller, but I controller has some disadvantages. So we can club actually these basic controllers to get their advantages and to nullify their disadvantages. So first let us go through the PI controller. So this is the transfer function of your PI controller, GCS equal to KP1 plus 1 upon TIS. And this is your controller. Here you can see this is the time domain equation. So this is your P part and this is your I part, and this is in the frequency domain equation. So that is the transfer function of your controller, GCS equal to KP1 plus 1 upon TIS. Here KP is known as the proportional gain and Ti is known as the integral time, and 1 upon Ti is known as the reset rate. So here you can see that the Ti affects the integral action while the Kp affects both, because Kp is present in P action as well as in I action. And obviously the advantages of both P and I controllers are clubbed together. So as we have seen that due to the P controller, the system response becomes faster, while due to the I controller, the steady state error becomes 0. So we are getting the advantages of both. So the disadvantage of the P controller that it cannot handle the ESS, it also gives offset. The same are removed by the I controller. So disadvantages are eliminated while we have the advantages in hand. So when Ti is increased, the damping factor zeta is also increased. So therefore, because of the large zeta, the oscillations are also reduced. So that make a system more stable. So here we can compare the responses. So for the same plant transfer function, we take this transfer function of our controllers. So this is our P part and this is our I part. So this blue one is your uncontrolled system. So here you can see that we have the ESS, the huge ESS we have, but with help of the PI, this ESS has reduced to 0 because the response has now reached to 1. So ESS is 0 now. Also, there is a reduction in the rise time, TR. So my system has become faster, and but there is a slight increment in maximum overshoot. Okay. So here we are getting the two advantages simultaneously. One is that the steady state error is completely removed, as well as we have a faster system response. So that is the advantages of PI. So now let us go through the PD controller, that is a proportional and derivative controller. So this is its transfer function, and this is the time domain equation. We can see that this is the P part, I mean the error is multiplied by some gain Kp, and here this is the D part where error is differentiated, I mean the input is differentiated then multiplied with the gain part, and this is the frequency domain equation. So this is the transfer function of your controller, that is Kp plus TDS. It is simply you are getting this equation by taking a Laplace transform of this equation. Here Kp is obviously is a proportional gain, and the TD is known as the derivative time. The advantages of both P controller and the D controllers we are getting here. Because of the P controller, we are getting the fast response, but it cannot handle the steady state error and produces offset too. Because here both are not able to reduce the steady state error. P is also not able to handle it. D is also not able to handle the ESS. So both are not able to handle or reduce the ESS. So we are going to get the steady state error in the response of the PD, although we get the fast response. Also the PD controller increases the damping factor zeta, and because of that the transient improves. I mean we get the less oscillations in the output. So that is helpful to make system response more stable. Also the PD controller has one more problem. It amplifies the noise signal also if they are present in the system, and it may cause the saturation effect in the actuator because of that impulsive behavior. So now let us compare its response with the uncontrolled system. So again we are taking the same plant transfer function, and this is the transfer function of our PD controller. So this is your the P part and this is your D part. So this is your uncontrolled system which has ESS, you can see, and this is the output of your PD controller. So again we have the steady state error in the response because both P and D cannot handle the ESS. So that is because of the offset of P controller, and here we can see that the system has become much faster because the rise time has become much lower as compared to the uncontrolled system. So system becomes much faster with the PD controller, but the ESS is still there. So that is the problem of PD controller. Now let us see the very popular form, that is a proportional, derivative and integral controller. I mean the all three are clubbed together. So it's a transfer function of the controller, and here we can see that this is the time domain equation. So this is the P part where air input is simply multiplied with the gain Kp. This is the D part where input is differentiated, then multiplied with the gain, and this is the I part where the input error is integrated and multiplied with the gain. And this is the frequency domain representation. So that is the transfer function of your PID controller. So here again the Kp is your proportional gain, and the Td is the derivative time, and Ti is the integral time. So we have already used these three terminology in the previous slides. Now the advantages of all the three, I mean the P, I and D controllers are clubbed together in the PID controller. So it gives faster response due to the P and D. Both P and D makes the system response faster, and the zero steady state error we get because of the I controller, and also because of the D controller we have the high value of the zeta, so that improves the transient. That means that reduces the oscillations and we get the higher stability. So that's why it is making the PID controller as the best among of these, because we have the advantages of all the three P, I and T. So also to achieve the desired response, PID controller must be fine-tuned. I mean the finding the optimal values of this Kp, Td and Ti, so we can get the best response. And here we can again see the performance comparison. So for the same transfer function, system transfer function, this is our PID controller. So this is your P part, this is the D part, and this is your integral part. And this blue one again is your uncontrolled system response. So it has the hues ESS, non-zero ESS, and here this is the response of your PID. So you can see that the ESS again is 0 because that the I in the PID is making it 0. Both P and D cannot make it 0 as we have seen. And also the system becomes faster. So you can see the rise time is decreased, so system is more faster. And also you can see that oscillations are quite controlled as compared to the previous examples. So the very less oscillations you can see in the PID. So the PID is giving a very much balanced output as compared to the previous categories. This is actually the implementation of the PID, or you can see the PID structure. You can make the PID controller in this parallel form. So you have the three subsystems. I mean this is your P, this is your integral, this is proportional integral, and this is your derivative system. So you can make this type of connections to realize your PID controller. So that structure is also useful when we are realizing this PID controller using some hardware or let's say some electronic components. So we can make three systems separately, and then we can make this type of parallel connection to realize it. And now let us see how we can design and tune a controller in the MATLAB. So MATLAB has this function that is the PID tune. So this is the plant transfer function, and this is type means you have to define the type of the controller, whether it is PI, PI, PD, PID, PID or PDF or PIDF. This is slightly different. Actually, it says that if you are using PDF, it means it will design a PD controller with a first order differentiator. Similarly, this is a PID with a first order differentiator. And we have options also. So in the options we can give some parameters, such as we can define the desired phase margin, such as the default is let's say the 60 phase margin, but if you want to change it you can define in options. Also you can define the design objective and the instability information of the open loop system, and the instability information of the open loop system that I will describe later. And when you execute this function, you get this output GC. GC is of course the transfer function of your controller, and info, it gives the information about the GC. That means its stability information, its omega g and phase margin with this loop gain GC, S and GS. So now let us see how we can use this PID tune in the MATLAB. So this is how we can define some transfer function. So this is some transfer function which is 1 upon s cube plus 3s square plus 3s plus 1. So this is some example transfer function, let's say, and we can define the options like this. The function is the PID tune option. So in this we can define the required phase margin. So phase margin, let's say 45 degree. So actually, as I said, the default is 60 degree, but you can change your requirement here. And the design focus is defined as a disturbance rejection. Actually, it has the two options. One is reference tracking and second is the disturbance rejection. So the default is the reference tracking. Actually, reference tracking is means that your output is following the reference point. So this is a very common type of control action, such as used in the let's say air conditioner or heat control in the oven. So where you set some reference point and your output follows that reference point. So that is all known as the reference tracking. And disturbance rejection is a different. Here our objective is to reduce the noise which is introduced in the system by some external source. Okay, and the number of unstable poles we have to define for the open loop system. So if your plant has some open loop systems which are in the positive right half of S plane, then we have to define the number of poles which are unstable poles. And then we can use this PID tune function like this. So system, that is your transfer function, and the PID type of controller we are designing, and then we are passing the options which we have achieved here. So when we execute this PID tune, we get the controller transfer function and its corresponding info in the info. So this is a very simple one. Now let us come to the MATLAB code for the implementation of these controllers. So here in the first line, I have taken the transfer function of the plant. That means the system open loop transfer function 5, 1, 6, 11, 6. It means it is realizing the same transfer function which I have already taken for all my previous explanations. That is 5 upon s plus 1, s plus 2 and s plus 3. And this is the second line is realizing its unity feedback system. So that means your plant G, and the unity feedback is given to the system, okay, plus minus, and then overall transfer function becomes now G upon 1 plus G. So that is your sys-CL. Okay, so it is the transfer function without controller. Now I am designing my controller. So first I am taking the PI controller. So I will use the PID tune function. So sys-OL, the open loop transfer function, I mean G is specified here, and the type of controller PI is specified here. So when it is executed, you get the transfer function of your controller GC and its information, corresponding information. And here we are just displaying these transfer function and information in the workspace. And now we are making the closed loop system with the controller. So this is the G and this is the GC. So G into GC and having the feedback 1. So sys-CL PI means this is the transfer function with the controller. So now I have GC, that is my controller, GC, and then my plant, that is the G, and then feedback loop, okay, plus minus. So here I'm getting my closed loop system. So that is GC G upon 1 plus GC G. So this transfer function is represented by this sys-CL PI, and this PI is realized by this GC. And now here I'm designing the PD controller. So again, with the same PID tune function, system open loop, that is your G, and this is the type PD. So I'm getting the transfer function in GCPD, and I'm doing the same action here. Again, I am getting the closed loop transfer function with the GC for the PD, and then I am designing the PID controller. So executing PID tune with the G open loop system and then type PID. So I will get the transfer function of the PID in GCPID, and then making a closed loop system with the PID controller. And then I am executing this step response of closed loop system with a step info function. So here when this is executed, you will see all the step response attributes such as rise time, peak time, maximum overshoot, settling time, etc. All the related informations in the workspace for the closed loop system without controller and the closed loop system with PID controller. And here I am plotting these responses using subplot. So this is plotting the step response of uncontrolled system, step response of your system with a PI controller, step response of system with a PD controller, and then step response of your closed loop system with PID controller. And in this separate figure, I am plotting the step response of all these closed loop systems. I mean the open loop system, closed loop uncontrolled system, system with a PI, PD and PID, all in the same plot for the performance comparison. So now let me run this program in the MATLAB and let's see what type of output I will achieve. So let me open the editor, and this program is already written. So I will simply press this run button to execute it. So it is executed, and let's wait for response. Okay, so I'm getting these plots. So in this plot you can see the individual responses of closed loop system with the PI controller, with PD controller and with the PID controller, and this is the response of your closed loop uncontrolled system, I mean without any controller. So in this case it is not possible to compare these all responses, so we can go to the second plot where all are plotted on the same window. So this is the plot where you can see all the responses together. Now let us go to the workspace to see the output of this program which we have displayed. So here we have achieved some output in the workspace. So here you can look at that GCPI equal to KP plus KI upon I. So that is a transfer function of your PI controller with a KP equal to 1.52 and KI equal to 1.01. Similarly, we have the transfer function of your PD controller GCPD, that is KP plus KD into S with a KP and KD value, and this is the transfer function of your PID controller with the KP and KD and KI values, and this is what we have achieved with that step info function. So these are the step response attributes of the closed loop system without the controller, and these are the step response attributes of your step response of the closed loop system with the PID controller. So you can compare, for example, if you compare the rise time for uncontrolled, it is 1.2598 seconds, and here it is only about the 1 second. So obviously the rise time has reduced. So with help of the PID controller you can say that your system has becomes faster. Obviously you can see that settling time is 3.84 in the uncontrolled system, and here the settling time is 3.3, so it is also reduced. And then we can see that overshoot is 7.5, that is in uncontrolled, and in PID controlled system it is only the 5.5, so it is also reduced. So you can see that there is a improvement with the PID controller. Also ESS is not given here because these are related with the transient part, and we have seen that ESS has becomes 0 in case of PID, though there is a huge ESS is observed with the uncontrolled system. So this is how we have achieved the improvement with help of controller. So now let me jump to the presentation for the comparison. So this is the output curve which we have just achieved in the MATLAB. So let us do a comparative analysis. So this blue one is actually the open loop transfer function. That means this is the step response of your plant transfer function GS. So that was your 5 upon s plus 1, s plus 2 and s plus 3. Obviously it has 3 poles, all are at real axis. So obviously this step response has no oscillations. So it is gradually increasing towards the final value, but we can observe the steady state error. So that is equivalent to this. It is not reaching towards 1, and also its speed is low. I mean, it is not faster because it is a overdamped system. And when we give the closed loop of this system with the unity feedback, we get this type of response. That means it is simply G upon 1 plus G response. So here we can see that its performance is further degraded. That means the ESS has further increased, and it has some oscillations are also introduced, and then it has become slower also. So the closed loop system is really performing very poorly. So now with help of the controller we can improve its response. So how we can improve its response? So when we apply the PI controller, you can see that this orange one is the step response with the PI controller. So you can see that the ESS becomes 0 because the response has reached to 1. So here ESS is 0. Also it has shifted to this side. It means your rise time has reduced, so your system becomes faster as compared to your uncontrolled system. And also some oscillations are introduced, and this MP is introduced. So that is some disadvantage of this PI, but we are getting the 2 advantages here. One is that the steady state error is 0, as well as the system has become faster. Now with the PD controller, this purple one, you can see there is a huge reduction in the rise time, and the system is now fastest. So because of that D controller and P controller, also amplitude of the oscillations is increased. That means the maximum overshoot is increased as compared to this uncontrolled. And because of the high zeta, although these oscillations are dying out in very less time, but the problem with the PD control is that the ESS is not reduced to 0. It still has the steady state error. And now let's see the last one, that is a PID controller, this dash line of red color. So here we can see that it's reaching to the 1, so it has a steady state error 0. Also it is faster than uncontrolled system, as well as the faster than this PI controller, but not faster than this PD one. And also its peak overshoot is also not large as compared to this PD and PI, and oscillations are also very less. So the PID controller is giving a very balanced and optimum output as compared to others. So that's why PID controller is known as best among this category. So now let us summarize all these points. So we can see that the uncontrolled system has the largest steady state error, and with a PI controller, this steady state error becomes 0, and system becomes faster. Okay, system becomes faster, and but some oscillations are also observed. And with a PD controller, the system becomes fastest, but the steady state error is still there. It is not able to reduce it to 0. And then PID controller reduces the steady state error to 0, and also it is faster than the uncontrolled system, as well as faster than the PI, and also it has the less oscillations and less maximum overshoot. So the PID controller is giving the best response among all these controllers. So that's it for this video. I hope you have enjoyed it and learned the concepts about these controllers, particularly the PID controllers. So I really thank you all for watching this video, and please like it, share it, and stay tuned for more such interesting videos to come. Till then, goodbye.